Okay. So the initial speed is this. Now, keeping the radius constant, the tension in the string is double. Keeping the radius constant, the tension in the string is double. Okay, so we have T1, which is equal to T. But for T2, this is equal to 2 times T1. Now, so it's like you write an equation for both situations. We know when an object is tied to a string and held, the centripetal force is provided by the tension within the string. So T is equal to mv squared on r. But we won't use this because they are talking about angular speed. And in angular speed, it means we must express the centripetal force in terms of angular speed, which we have done. And this is m omega squared r. This is also centripetal force, but so the question says that the mass, okay, so T1 would be equal to 2 mass of 2 times initial angular velocity 5 revolution per minute times radius. Now T2, in T2, this is equation 1. So maybe if you want us to do something, this is 25 times, so 50 R for T1, equation 1. In the second situation, the tension is double. So T2 would also be equal to M doesn't change. Omega 2 squared, R is also constant. Please let me change the marker. So radius is kept constant. So T2, in T2, the tension is 2 times the first situation. So 2 times T1 will be T2, which is equal to mass is constant, but we don't know omega 2 when you double the tension. R is also constant. So this is equation 2. Okay. Now, divide equation 1 by equation 2 because we are looking for the angular velocity or angular speed when the tension is double. So T1 over 2T1 is equal to 50R over 5 times omega 2 squared times R. So this and this will cancel. This goes into 5010. Okay, T1 will cancel. So we have 1 on 2 is equal to 10 divided by omega 2 squared. We are looking for omega 2. So omega 2 squared will be equal to 10 by 2, which is 20. Therefore, omega 2 will be equal to square root of 20. And square root of 20 is equal to 2 root of 5. What is 2 root 5? Plus, what is 2 root 5?
4.472.
So I think this is giving us a different thing. Let's go through
472.
Let's see what happened. In equation 1, mass is 2 times 5. So this is 25 times 2, 50 R. In equation 2, tension is doubled. So 2 times T1 is equal to, Charlie, you people do not also follow. The mass is 2, but I made it 5. Equia, Kenneth, you people are not observant. The mass is 2, but I made it 5. So this must be 2. So if M is 2, then we'll have T1 equal to omega 2 squared R for equation 2. We just cancelled. So if you take a ratio of equation 1 and equation 2, you have T1 on T1. I'm dividing the left-hand side by, and then the right-hand side is equal to 50 R divided by omega 2 squared R. And the R's will cancel out. Okay. T will also, so this is omega 2 squared is equal to 50. Omega 2 therefore is equal to square root of 50, which is 5 root of 2. And 5 root of 2 will give us whatever we had earlier. So that's the answer for. And this is giving us approximately 7.0 revolution per minute. So that's the solution for the question 1. Question 2. Akwi, are you there?
Yes, sir.
Why you doing? As for question 50, the answer is there. Okay. It's that the magnitude of the centripetal force acting on a body of mass M executing uniform motion in a circle of radius R with speed V S. Yes, Adwa Otubia, what will be the correct answer?
Yes, to be MV squared by R.
MV squared over R. Okay. That's true. Question 51. Kenneth, are you there?
Yes, sir.
A string breaks if its tension exceeds 10 Newton. So the maximum tension is supposed to be 10 Newton. A stone of mass 250 gram tied to this string of length. So maximum tension, T maximum, is giving us 10 Newton. Then a stone of mass 250 gram. So mass of stone 250 gram tied to this string of length 10 centimeter. So the length of string is 10 centimeter. It's rotated in a horizontal cycle. It's rotated in a horizontal cycle. The maximum angular velocity of rotation can be, so we are looking for the maximum angular velocity. Okay, so still T is equal to m omega squared r. So if this is the maximum tension, maximum angular velocity, omega squared maximum would be equal to T over mr when you divide through by mr. Therefore, we have 10 over, you need to change the mass from gram to kilogram. So 1, 2, 3, 0.25 times the radius is equal to the length of the string. So this will also be 0.1. So help me calculate for this. 10 divided by 0.25 times 0.1. Adwa.
It's 400.
Come again. Adwa, I can't hear you.
This is 400.
So this is 400. Therefore, maximum angular velocity is equal to square root of 400, which is 20. Okay, so 20 radian per second. So it looks as if,
Mr. Dia.
hello.
So there in the question, it stated velocity. So can't you use c is equal to mv squared over r to solve this?
What the question stated velocity. There's the maximum angular velocity. It's the maximum angular velocity, not just the velocity. Okay. I want you to try question 52, all of you. A 500 kilogram car takes a round turn of radius 50 meter with a velocity of 36 kilometers per hour. The centripetal force is, I want you to do this in about 5 minutes time. A 500 kilogram car takes round turn of radius 50 meter with a velocity of 36 kilometers per hour. The centripetal force is even 5 minutes for this is so much. Yes, what have we had? Kenneth, what have you had?
Sir, please, 1,000 newtons.
1,000 Newton. Adwa. Adwa, what have you had?
It's 100,000.
100,000 Newton. Okay. Akuya, what have you had?
1,000 Newton.
1,000 Newton. Obenewa, what have you had? Obenewa, are you there? Inshira, what have you had? Inshira. Janice, what have you had?
100 newtons.
100. Okay, Nanama. Nanama. Okay. Then let's look at it. So the mass let me change my marker paper. Okay, so the mass is 500 kilograms. So M is 500 kg. Then the radius is 50 meter. The velocity is 36 kilometer per hour. And this is the only problem area because you must convert everything to SI units. So we just would have to change the velocity from this to meter per second. So 36 times 10 to the power 3 m over 1 hour is 3,600 seconds. So the velocity is actually equal to 10 meter per second. So if V is this, then the centripetal force will be, which is mv squared on R, is equal to 500 by 10 squared over a radius of 50. Okay. So we have 1,000 Newton to be the centripetal force. So it isn't any difficult question, but you need to understand what to do. If once other values are given in SI, you must convert all other units to SI unit and then work with it. Okay. Then a wheel completes 2,000 revolutions to cover the 9.5 kilometer distance. The diameter of the wheel, therefore, is, I want you to do this, 5 minutes. 5 minutes, I'll come back to you. A wheel completes 2,000 revolutions to cover a 9.5 kilometer distance. The diameter of the wheel, therefore, is. Let me see how you can apply to answer.
Sir, please, can you take the question again?
No, the question is on the platform. The question is on the platform.
Okay.
We are answering the questions I sent to you on the platform, which you never attempted. I've reposted it, so a wheel completes 2,000 revolutions to cover 9.5 kilometer distance. The diameter of the wheel, therefore, is. You must be through by now. Yeah, it's true. Who is true? You have 2 minutes. Kenneth,
Yes, sir.
what have you
Sir,
had?
please, I got 0.0015.
Equia,
So, please, I had 23864 times 10 raised to the power 4 meters.
hey. Adwa,
I had 1.501 meters.
Janice,
15.1 meters.
okay. Obenowa, Abenowa is not responding. Immaculate, did you try? Hello, please, I'm coming in. Let me pick something and come. If the wheel completes 2,000 revolutions, please, what is this value? The 2,000 revolutions, what does it represent? The 2,000 revolutions, what does it represent?
Sir, please, angular displacement.
Angular displacement. So it completes 2,000 revolutions. So theta is equal to 2,000 rev. And it covers a distance of 9.5 kilometers. What is this value representing? The 9.5 kilometer, what does it represent? Class, the 9.5, which distance? Which distance?
Linear.
So linear displacement, S. And the question requires the diameter. Okay, so let's change everything to SI unit. So this is 2,000 times 2 pi radian. This is also 9.5 times 10 to the power 3 meter. S therefore is equal to R theta. So the radius is equal to S on the angular displacement. So we are talking about 9,500 divided by, this is 4,000 pi. What will be the value of 1212? So we are talking about 95 on 40 pi. What is 95 on 40 pi? Give me this in decimal. Give me this in decimal.
0.755.
0.755. Diameter is equal to 2 times R. So we have 2 times 0.755, which is, that will be 1 point what?
5.1.
So that's the diameter. That's the diameter. Then a string of length L is fixed at one end and carries a mass capital M at the other end. So the length of the string is L. Length of string L, and then the mass of string capital M. The string makes a 2 over pi revolutions per second. So the angular velocity omega is equal to 2 over pi rev per second, RPS. Okay. I image this angular velocity around the vertical axis through the fixed end as shown. Then the tension in the string. We have to determine the tension in the string. Okay. This is a typical example of conical pendulum. The diagram shows a conical pendulum. And in conical pendulum, we have either the tension, the T sine theta equal to, the T sine theta is equal to, yes, T sine theta is equal to,
Sir, please, the centrifugal force. Centripetal
So-
force.
the centripetal force, M omega squared R, or mv squared over R. I'm representing it as this because we have angular velocity within. We have angular velocity within. Then the radius of the cycle is also L sine theta. If you recall, look at those formula we derived. So we have T sine theta equal to M omega squared L sine theta. And so sine theta would cancel out. So we have the tension T being equal to M omega squared L. The mass is capital M. Angular velocity is 2 pi this. So we have 2 over pi squared times the length L will be the tension. And so the tension T would be equal to 4 M L over pi squared. This will be the tension within the string. Here we are not converting because other variables are not given. We don't have the real values of these variables. The reason for us, or if we can, let's convert because the possible answers there, ours isn't in. So if we have angular velocity of 2 on pi rev per second, this will be equal to times 2 pi radian per second. Please, are we following it? I'm trying to change the angular velocity, which is given in revolution per second, to radian per second. So we simply have, yes, 2 over pi rev over 1 second. So the denominator, the time is in seconds. So our worry is about this. Okay. Now, one revolution is equal to 2 pi radian. So all that we are doing is that, okay, then we have 2 over pi times 2 pi radian. Okay. And that is in converting this to radian. This is radian per second. So in effect, what we have for this is actually 4 radian per second for the angular velocity expressed as such. So, and so therefore the tension T is equal to M times, we changed this and we had 4. So 4 squared times L. Therefore, 16 mL is the tension in the string. 16 mL is the, so it is the option D. The answer is the option D. Please, are we okay? Class, are you fine by the solution?
Yes, please.
So it's a step-by-step thing, okay? And over here, I didn't equate T cos theta to mg because I didn't do this because this has nothing to do with angular velocity. I was given angular velocity omega. But when I equate T cos theta to this, this has nothing to do with angular velocity. And so the obvious one must be T sine theta connecting to the centripetal force within which we have m omega squared, or within which we have the angular velocity. All right. So let's continue from where we ended in our last meeting. Please, what I want you to do is that spend time to go over the questions as we have solved. Go through it, okay? Look at it step by step. That will help you apply the concept learned in solving problems and just writing it without going over. So at your free time, that's what I want you to do for me. We were looking at vertical oscillation or circular motion in the vertical plane last time, where we looked at maximum velocity, so maximum tension, and then minimum tension in a string. So we looked at some key aspects of the motion. When the body is vertically upwards or up the circle, what happens? When the body is down the circle, what happens? And I'm talking about when oscillation is along the vertical plane. So let me indicate the center very well. So here we are looking at something like the body revolves in an anti-clockwise direction. So oscillation along the vertical plane or vertical circle. Then we determined the tension within the string at E, this point. We also determined over here and then over here. This has the same level as this. Okay. And we came to the realization that when the body is here, maximum tension occurs within the string because the net force A, B, C, D, the net force is equal to T minus mg. The net force is directed towards the center of the circle, and so that provides the centripetal force. T at this point, therefore, is equal to mv squared over r plus mg, which give us v squared over r plus g. And so we realize when the body is below the circle, maximum tension, T maximum, occurs within the string. So when the body is below the circle, maximum tension occurs within the string. So this is at E. Then we looked at when the body is above the circle at C, we also drew the analysis that the weight acts downwards, mg. The tension acts towards the center. And so at C, the net force is given by mg plus T. And since this net force has a direction towards the center and along the radius, we equate the net force to the centripetal force, which is mv squared over r mg plus T. When you make T the subject, you have mv squared over r minus mg. And this is equal to m out v squared over r in minus g. And so we came to the realization that when it is the body or the mass is above the circle, minimum tension occurs within the string. Okay. At B, we drew the conclusion that when the body is at B, the tension in the string is equal to the centripetal force mv squared over r. Please note that we can equally equate centripetal force to be m omega squared r. So it can be either mv squared on r or m omega squared r. Now, what I'm adding is that, so when the body moves from this point to this point, it's like having gone through an angle of 90 degrees. So at 90 degrees, the tension is equal to this, mv squared on r. At 180, when the body has moved from this point to this point, the tension is equal to minimum. Okay. Now, what if the body is in between at any angle theta? The body is here. And so the angle it makes with this vertical is just theta. How do you determine the tension in the string? Because we have looked at the tension when the body is here, 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 and here. Standard angle. But if it is at any angle, maybe 30 degrees, it makes an angle of 30 degrees with a vertical. What will be the tension within the string? 20 degrees. That is the next thing to look at. And when you get that, you can apply it to all other positions of the body. Please, are you there?
Yes, please.
Yes.
So let's look at any angle theta, how do we calculate the tension within the string? There's the mass, its weight always follows gravity. Now, when we extend this weight vector, we realize that this angle alternates with this angle. So if this is theta, this will also be theta. Now let's extend the tension within the string always acts toward the center. So let's extend the tension line. If we extend the tension line, if this angle is theta, this will also be theta, vertically opposite angles. Okay, vertically opposite angles. mg. Now, if I have a bird on top of a tree, there's the ground, and I want to look at the bird on top of the tree, then I must turn my eye, elevate it by this angle. So I must elevate my eye level by this angle. Okay, so this becomes the angle of elevation to enable me view the bird on top of the tree. Because of this, the angle is measured from the reference, which is the horizontal, to the hypotenuse. And so this side becomes the adjacent to the angle, the adjacent side of the right angle triangle. Now, when you identify the adjacent, a perpendicular line to the adjacent becomes the opposite. So once you identify the adjacent, if you draw a perpendicular line to it, you have the opposite. So this side becomes the opposite, the adjacent, and this is the hypotenuse. Let's apply it here. The angle, this angle is measured from here to this side. And so when you draw a line, this side becomes the adjacent. Okay, when you identify the adjacent, a perpendicular line from the adjacent gives you the opposite. So this is the adjacent, the opposite, and then the weight vector becomes the hypotenuse. So we have weight inclined at an angle theta. We want to resolve to get the adjacent. We are only interested in the adjacent. Okay, we are only interested in the adjacent. Fine, we can determine the opposite as well. What will be this component of the weight? The adjacent. What will be this component of the weight? If this is the hypotenuse, there's the angle. What will be the horizontal or the adjacent? Yes. Somebody to tell me what will be that horizontal component of this weight. I'm waiting. The horizontal or adjacent of the weight mg.
Yeah, please, it will be mg sine theta.
mg in cos theta.
It will be, yes, it will be cos. So this side is mg cos theta, and the opposite becomes mg sine theta. So this side of it is giving us mg cos theta. Now, look at the mass and then the vertical forces acting on the mass. We have mg cos theta acting downwards and t acting towards the center from the mass. Okay, whenever two forces come to play, there will always be a resultant force. So we want to determine the resultant force. The resultant force, because this body is in circular motion, okay, it means T, the tension within must be greater than mg cos theta. If T isn't greater than mg cos theta, it can tear off and the body would fail to be in circular motion. So for circular motion to occur, T must be greater than mg cos theta. Therefore, the net force between T and mg cos theta becomes T minus mg cos theta. The net force always acts in the direction of the larger force. Okay. The net force always acts in the direction of the larger force. So what will be the direction of the net force? Yes. I'm taking the statement again. The net force always acts in the direction of the larger force. So what will be the direction of the net force here? Hey, did you get a question? I gave you a preamble. The preamble is that net force always acts in the direction of the larger force. So what will be the direction of the net force T minus mg cos theta?
In the direction of tension.
So towards the center. The tension is directed towards the center. So the direction of this net force is towards the center, also along the radius. Because of that, we equate the net force to the centripetal force. Because centripetal force acts towards the center along the radius. So if we have a net force, okay, with the same direction, then that must be equal to the centripetal force. So let's make T the subject. T is equal to mv squared over r plus mg cos theta, which can be simplified as m out v squared over r in plus j cos theta. And this is the expression for the tension at any angle theta. So when the string makes an angle of maybe 30 degrees with this vertical, calculate the tension there. All that you must do is the velocity at this point, the v, the mass times v squared over the radius. The radius is the length of the string. Okay, then you put in cos of the angle given. Now, we can also use the same relation to find the tension here, as we've done already. So let's just recap the same thing. So this is more or less a general formula. If the body moves from A to B, what is the angle covered here? If the body moves from point A to B, what's the angle covered?
-90 degrees.
So theta is 90. If theta is 90, substitute it into this relation. T would be equal to m out v squared over R plus J cos 90. Cos 90 is 0. And so all this part goes to 0. So we have T equal to mv squared over R. And that is what I said earlier, that when the body is here, the tension provides a centripetal force. So T is equal to that. When it moves from A to C, what is the angle covered?
180 degrees.
So theta in this case is 180 degrees. If theta is 180, then T is equal to mv squared on R plus J cos of 180 degrees. Cos 180 is equal to -1. So we have m out v squared on R in minus G. And this is what we were terming as the minimum tension. So it is giving us the same formula as we considered earlier. When the body is at D, because it's at the same level as B, the tension here will be the same as the tension here. Okay, now when it is at D, theta is equal to 270. Put 270 degrees into the equation. Let's see what you get for the tension. What did you get for the tension there?
Mr. Please, I got T is equal to mv squared on R.
So it means that once it is at the same level as B, there will be the same tension, okay, acting at both ends. So the tension at B will be equal to the tension at D because they are at the same level. Now, when the body revolves and then comes back to A, what is the angle? What is the angle here? When the body revolves and then comes back to A, what is the angle?
360 degrees.
So theta is 360. If theta is 360, put in 360, let's see what you have for the tension.
When you put it in, you get 1. So tension will be equal to mv squared over R plus mg.
That's the same relation as we have derived before. So all that I'm trying to say is that at any angle theta, which is this relation, is general. It's a general formula to determine tension at any point. Okay. So if a question is given and the question says that calculate the tension, you are giving speed, blah, 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 and you're asked to calculate the tension at an angle when the string makes an angle of 30 degrees with a vertical. This is, you use this. Any question? Any question? Okay. Then let's move on to the last stage of circular motion, which is banking of roads. Banking of roads. Hold on, let me see if I can get a question on this so we can try, okay? We can see how to apply it in solving problems. So give me a write the question. An object of mass 8 kilogram. An object of mass 8 kilogram is whirled round rapidly. In a vertical circle of radius 2 meters. In a vertical circle of radius 2 meters. With a constant speed of 6 meters per second. With a constant speed of 6 meters per second. Calculate the maximum and minimum tensions in the string. Calculate the maximum and minimum tensions in the string. Take J to be equal to 10 meters per second squared. So about 3 minutes, just give it a try. They are turning at a very sharp curve. And it's a competition. If you want to turn, you cannot reduce speed because it's a competition. But you reduce, by the time you finish, somebody who understands how to apply these tricks will just turn and go, leave you. So for them to be able to ride at that top speed, they need to turn the bike at an angle in order to provide something extra, okay? Something extra. They do that to get something extra, which will provide centripetal force. So as they turn the bike at an angle, all that they are doing is that they are doing something extra to provide a centripetal force. Something must augment the centripetal, because we learned that whenever a car, bicycle, or a motor negotiate a bend, the centripetal force is provided by the frictional force between the road and then the tires. But frictional force has a limit. Okay, it can only help with some speed. If you are speeding so much and you want to turn, the frictional force will not be enough to help you turn. And so they have to create an intervention which will add to the frictional force to enable them turn. The reason for that turning of the bike and their body at an angle. So all that they are doing is that they are providing something extra which will enable them move at that top speed and still be able to make that turn so that the motor will not skid. Please, are you okay? Are you okay?
Yes, sir.
So this is a circular path. A curvy road. So it isn't for life. No. A motorist who want to make this turn. So there is the motorcycle. What are the forces acting on the motorcycle? We have its weight, mg. Then we have the reactional force provided by the surface, r. Now, he turns the bike through this angle theta to the vertical. It can also be to the horizontal. Okay. So this is the banking angle, the angle through which he has to turn to the vertical. So when we have the reactional force acting here, we have the banking angle theta to the vertical. When you resolve this, you have r cos theta. There's the adjacent. The opposite, r sin theta, we'll bring it here because of equal vectors. So instead of indicating the opposite here, we'll bring it here, r sine of theta. So when the cyclist or the motorist turn at an angle theta to the vertical, okay, we have these forces acting on the reactional force provided by the ground. Its weight is here, and then this is the angle of tilt to the vertical. So mg r cos theta acts upwardly, and then r sin theta acts. This is a curvy road. This is a curvy road, and so this r sin theta acts towards the center of the circular road. So the r cos theta is balanced by the weight of the cyclist and then the cycle, mg. Then the r sin theta is unbalanced. It has no balancer at the opposite end, no. So we say this is unbalanced. But this component, which is unbalanced, has a direction towards the center and along the radius. So we equate it to mv, the centripetal force, So, when the cyclist or the motorist turns, that additional component to the frictional force is the R sine theta. So this is what adds up to the frictional, if there is friction on the surface, this is what adds up to the frictional force on the surface to enable the cyclist or the motorist make the turn with that top speed. If he doesn't do this, he would have to rely only on friction to turn. And if he is relying on only friction, then he cannot embark on that top speed. He must reduce speed to make the turn. May class, we are not friend. Okay, so the R sine theta component of the normal reactional force, please indicate where R is the normal reaction or reactional force. Okay, the R sine theta component is what supplies the added centripetal force. Please, if you have any question, ask. Let's extract a very important equation. So R cos theta is balanced by the weight. R sine theta is equal to the centripetal force. Now divide let's divide equation 2 by equation 1. So R sine theta, left hand side divided by left hand side over R cos theta is equal to mv squared on R, also divide by this. So we have R and R canceling out. Sine theta over cos theta is equal to tan theta. We have V squared over RG. If we make E the subject, it is giving us the same relation as we saw in conical pendulum. And this gives us an expression for the maximum velocity. So with this expression, we are looking at when the driver makes that turn, okay, when he turns the bike at an angle and there is almost zero, the frictional force on the surface is so small, negligible. So this is for without depending on friction. We will look at when we are considering frictional force at the surface or on the surface of the road, what will also be the expression for Vmax. So for banking of roads, when frictional force is almost negligible or is ignored, then the maximum speed, okay, the maximum speed must be anything less or equal to Rg tan theta, meaning that this maximum speed depends on square root of the radius of the road. If the radius is large, the speed can also be increased. It's also, the maximum speed is also directly proportional to the square root of the tangent of the angle of tilt. Meaning, if you could turn well, tilt the motor to have a larger angle, it will also increase the speed. The reason for which motorists make that turn as if they are almost falling, because the speed you can move with or move by is directly proportional to the tangent, square root of the tangent of the angle of tilt. So if theta is large relative to the vertical, then it can also augment your speed. So if you are speeding so much and you want to make that sharp turn, then be ready to, turn, okay, to the level as if you are almost dropping to the ground. This is the whole essence of it. So this is the expression of maximum velocity. The maximum velocity depends on the radius and then the angle of tilt. Please, another question. Any question? All right. If there is no question, then I think what is left under this, we have to look at cars. Okay, let me talk about it, and then so that in our next meeting we'll have something, we'll just solve questions on this. Motors can make the turn. Bicycles can turn. But if you are riding a car or driving, whenever you turn within the car, it will never turn the car, because the car is 4 wheels. So for 4 wheels, if drivers would have to, speed and then still make a sharp turn, they cannot only turn within to provide that additional centripetal force, because this is about 4 wheels. You can only do that for 2 wheels, bicycle, motor, but 3 wheels, 4 wheels, when you turn, it will not turn the car. So the road must be designed, okay, to factor that. And that is the whole essence of banking of roads. For this one, 2 wheels can do it. The driver or the rider can turn the bicycle, turn his body, and so will turn, okay, the bicycle or the motor. But 4 wheels, it cannot be done unless the road is designed to do that. So when you are traveling on the road, where the road is so curvy, okay, where there's a sharp curve, the road is banked. Banking of road is such that because we want to make the car turn, the road is built in such a way that the outer end is raised in order to make a certain angle with the horizontal. So the outer end of the road, curvy road, is raised. And so when cars or motorists are moving on such roads, the car is tilted. The car is already tilted, so the road is inclined toward the center. So banking a road simply means building a road banking of roads. Is the architectural design where roads are built in such a way that it is tilted at an angle towards the center of the road. So here, it is an architectural design where the road is built, okay, in such a way that it is tilted at an angle, theta, towards the center of the road. Or the outer end of the road is raised so that it makes an angle theta with this horizontal. I don't know if you have seen banked roads, okay, before. Have you seen an area where the road is banked before? I'm asking you, have you seen an area, a banked road on a road network before, where the road is built in such a way that it is tilted at an angle towards the center? It is often seen at curvy roads, where the road is curvy or where there's a sharp curve. You find the road being banked. I'll send you videos of roads that are banked for you to have a feel of how it is. Okay. So in our next lesson, we'll look at what also provides the centripetal force. Yes, it is still the R sine theta, but how does it go with cars? When there is friction, when there is no friction, how does it, go? And how does it, or how is the maximum velocity or speed calculated in each case? Is that okay? For banking of roads. We've done that for where motorists would have to tilt the motor or the bicycle to provide the additional centripetal force. But for cars, a road must be designed, okay, to supply that. So we'll go into it and then look at the mathematics and then the physics of it. Okay, but we'll end here. It's exactly 8:54. This is where we'll draw the curtains on today's meeting. If you have any question, ask. If you don't have any question, then we end here. Epia, do you have any question?
No, sir.
Okay. All right. Then, Epia, will you be coming tomorrow